So I will give some definition related to semiconductor photocatalysis. And I will start from the very beginning, since it's placed in the fundamentals section. And so, starting from which is the definition of a semiconductor. It's materials whose conductivity falls between those of insulator and metals, and in particular, those which present a band gap, a separation between the last occupied valence bond and the first unoccupied by electrons band that has an energy gap comprised between 1 and 5 electron volts. Which are the key properties that we have to keep in mind when we are developing photocatalysis using semiconductor? The first things that we have to face with is, of course, the energy gap, and so which is the excitation light that we need to apply for promote electron from the valence bond to the conduction bond, and so to create the oxidoreductive species. This is the first point that we have to take in account, and since we are using it as photocatalyst, we need to know exactly which is the photon energy with which we have to work on. And so we need to calculate which is the minimum lambda that is needed to achieve this formation of active species. If we work with low energy gap, this is good because we can use solar light, and so use the photocatalyst as a cheap technique. But in this case, if we are working with very low energy gap, we have the problem that most of these semiconductors are not stable. Some of them may photocorrode, and so keep in mind that this is one of the side effects related to working with very low band gap. Oh. The second key property that we have to keep in mind when studying semiconductor photocatalysis is the position of the valence and the conduction bands, since those positions are linked to the oxidative and reductive capacity of the system. If we consider some of these semiconductors that are those that are widely used, have been widely used since the birth of photocatalysis, we can see that if we look at the energy position relative to the conduction band, we have a lot of semiconductors that present this band at a very high potential, and so we can use favorably photocatalysis to obtain oxidation processes. But if we look at the position of this electron band, conduction band, in this case, we can see that only few of them present a very negative potential, and so is suitable, is very active in promoting reductive processes. In particular, if we look in depth to what happened to the surface of semiconductor, first of all, we have to deal with the Fermi level. That is the redox potential in a semiconductor. And if we are dealing with an intrinsic semiconductor, so a pure semiconductor, in this case, the Fermi level is placed in the middle of the energy gap. But since usually intrinsic pure semiconductor present a very low conductivity, we are working always with doped semiconductor. We can have doping with an excess of electrons, so we have a donor level that is placed very close to the conduction band, and in this case, the Fermi level is shifted very close to the conduction band. In this case, the majority carriers are electrons. In the other case, if we are working with an excess of holes, we are dealing with an acceptor level that is placed very near to the valence band, and consequently also the Fermi level is moved very in depth close to the valence band. We can have two essentially two main kind of semiconductor doped. The first one are the intrinsic doped semiconductor, and within this category falls most of the semiconductor that are frequently used in photocatalysis. We can recognize as N-type titanium dioxide, zinc oxide, as P-type, for instance, copper oxide. Or the other possibility is to have extrinsic semiconductor doped with some external elements, with some impurities, characterized by possessing a higher or lower electrons valence. In this case, if we consider the basic case of silicon, we can have doping, for instance, with the phosphorus, so with creating a reservoir of electrons. And in the opposite case, if we dope with fewer valence electrons bound element as gallium, we have an excess of holes. So, considering these first two features of the semiconductor, what we have, we can have different cases as depicted in this graph. We can have some conductors with a medium band gap, and in this case, for instance, we can use UV, and in particular, a small portion of solar light. And if we consider its oxidoreductive potentials are almost good. If we move to a semiconductor with a larger band gap, in this case, we have a very good oxidoreductive properties. So we are working with a very important aspect, but the UV light that is needed to obtain excitation in this case exceed this present in solar light, and so we need to use for sure UV light. In the other case, if we have a small band gap semiconductor, we can absorb visible light and so use very well solar light. But in this case, of course, we are reducing its oxidoreductive capacity. So this is one of the key problems when facing photocatalysis. We are facing with a blanket that is always too short, and so we have to choose a compromise between these two opposite parts. And most of the work that start from this first beginning try to overcome this short blanket that we have. This is basically what happens when we are considering a semiconductor, a solid, but of course the solid is placed in a solution. We are working in this summer school, we are dealing specifically on water treatment, and so we have to consider the fact that our semiconductor is in contact with water and so with an electrolyte. And in this case, we can have different scenarios that present if we consider the different kind of semiconductor and of course kind of species that we have in solution. If we consider the case when we start with an N-type semiconductor, the first scenario could be this, where we have no space charge layer in the semiconductor. And so in this case, if we consider the conduction band electrons and the positive charge, they are balanced and we have no band bending. But if we have an excess of electron within the injection of negative charge in the semiconductor. In this case, we have an excess of electron that creates an accumulation level, and so we have a band bending toward the interface. The opposite case is when we have a negative charge at the interface, and in this case we have again the band bending, but that happens in the opposite side compared to the following case. This happens every time that we put in contact a semiconductor with an electrolyte, and of course what happens in the different cases is strongly related to the charge that we have in solution. And so, if we look in depth of what happened in this double layer, We can recognize a picture like this. So we have, again, we consider the case in which we have an excess of negative charge at the interface. So we can recognize a first layer that is called inner Helmholtz plane, where we have a chemisorption of the solvent. Then we have a second layer that is called the outer Helmholtz plane, where we have a physisorption, and then we have the so-called diffuse layer, where we can recognize our solvatate ions, that in this case are cations, as we have a negative surface. So, based on this, we can have different mechanisms that happens at the interface between semiconductor and electrolytes, and that can change the mechanism of charge transfer. We can recognize mainly three different kinds of charge transfer. The first one foreseen the direct transfer from the surface hole to the species that is very close to the surface, and so that is placed in the inner sphere. And this is the case where we have a very efficient charge transfer thanks to this intimate connection. The second case is again a direct whole electron transfer, but in this case that occurs in the outer sphere, so in the second layer, the outer layer. And so again, we can have a charge transfer, and the transfer of electrons follows the Marcus theory. The third mechanism is the one that foreseen the intervention of another species, and in particular, if we are working with a semiconductor that is in water, usually this species is OH radicals that can be absorbed at the surface or free in solution, but in any case, these radicals mediate the passage of charge from the substrate to the formation of radicals. This is what's happened basically at the interface, the three kinds of mechanisms that permit to obtain the charge transfer. But when we are looking at what happens in the surface, the semiconductor electrolyte interface, we have also to remind that all these reactions are, of course, dependent on pH, and so we have to know exactly which is the charge of the semiconductor for which we are dealing. And for such, it's important to know which is the point of zero charge of our semiconductor. If electrolyte is water, the point of zero charge is the point is the pH at which the concentration of OH is equal to concentration of protons. And if we have the case of water and the semiconductor is titanium dioxide, in this case the surface presents something like this. So we have hydroxy group, it's hydroxylated and hydrated surface. And if we consider how it changes the surface as a function of the pH, we consider that in this case we have pK1 that is 3.9, pK2 is 8.7, and so the point of zero charge for titanium dioxide is placed around 6. It means that in this range it is neutral, while if you are moving to a pH that is lower than the pH of zero charge, we have an accumulation of positive charge. And the opposite, if we are a pH that is higher than the pH of point of zero charge, the surface is negative charge. This what's happened if we have the presence of pure water, but you have to keep in mind that usually you are not dealing with the pure water. You may also have some other ions in solution that can change the surface, the charge surface, and so we have also to consider the possibility to exchange, above all the exchange of OH groups, and so the fact that we can have the formation of some other complex. If we consider the case of titanium dioxide, one of the ions that can be very easily exchanged with OH group is fluorine. This is the equilibrium that occurs, and if we look at the surface of titanium dioxide in this case, what we can see is that if we are in the presence of fluoride, we have an efficient transformation cover substitution of OH group with fluoride. And so if we are looking what happens by changing the pH, we can see that the charge, superficial charge, is positive only at very acidic pH. This is what's happened when we consider the normalized charge, while it's decreasing very, very soon and remains very close to zero, also at very acidic pH. So it's completely different compared to what happens if we are considered, for instance, titanium dioxide pure. And only when we are at a higher pH, so when we again have this unfavorable complexation of fluoride and we have again in the presence of pure titanium dioxide, we can have the normal charge surface that we are expected with titanium dioxide, and so with negative charge at higher pH. So these are some of the aspects that need to be considered. And if we take into account these properties, we can see which are some of the semiconductors that can be used and the range in which you can use this semiconductor. The first row presents some low band gap semiconductor that so can be easily excited using visible light, and so solar light. But most of them are unstable or are stable only in some range of pH or in some condition, as in this case, in presence of hydroxy sodium. While if we consider the lower part of the table, in this case we have several semiconductors that present similar band gap. All of them are stable, but present different point of the zero charge. So we have to take into account that the Fischer processes are, of course, modified accordingly. So what's happened basically, if we consider the primer processes at the surface. So we have our semiconductor. Following light irradiation, we have the formation of electron-hole pairs that can recombine in the bulk using giving heat dissipation, or they can migrate at the surface and in this case activate a lot of reaction. If we look in details what happens to a semiconductor particle, in this case we have in the bulk electron-hole pairs formation, then we can have recombination, and of course migration to the surface. In this case, if we are able to separate charge, and so we have the formation of a charge at the surface, we have the negative charge that if we are in water, pure water, we have oxygen that is able to scavenge most of the electrons that has been produced, while holes can react with organic compounds, for instance, of other species that can be easily oxidized. So this is basically the starting point from a reaction that involves semiconductor and photocatalysis. From this picture, we can have very different application. If we consider the exploitation mainly of oxidative reactions. In this case, we are able to oxidize most of the organic compounds, and so this is what's happened when we are treating waters. And hopefully, we are expecting to obtain mineralization of organic compound. It means transformation, of course, of organic carbon into carbon dioxide, but also the transformation of all heteroatoms in inorganic ions. In the case of sulfur, we have a formation of sulfate, phosphor phosphate, halide halogens. In the case of organic nitrogen, the picture of transformation is more tricky and is dependent on the oxidation state of the nitrogen in the organic molecule. And so you can have the predominance of ammonium, nitrate, nitrate, or nitrogen, gaseous nitrogen. If we are, in particular, we want to exploit mainly the reductive pathways, in this case, we have to be careful and find the proper suitable semiconductor. And so if we look of all the semiconductor that has been used, in this case, we have to choose among those that present a very high position of the electron, the conduction band. These are calculated pH 7, while not at 0 as usual. And so in this condition, we can see, to be sure that we can really exploit the reductive processes, we need to have very high, and in particular, the most favorable semiconductor is the one that permits also to reduce carbon dioxide. In the case we want to mainly use reductive pathway, this is the case in which we use it to obtain the reduction of carbon dioxide, and so the case in which we are mimic what occurs in photosynthesis, natural photosynthesis. This kind of reactions that is in a wide range of application of photocatalysis can be obtained using a semiconductor that usually present eco-catalysts and that permit to obtain a separate reaction involving carbon dioxide and evolution of oxygen from water. This, as Marco told before, is a non-spontaneous reaction, and so we have to face with the problem of search for proper semiconductor that is able to induce this reaction. Usually, we are not dealing with this direct transfer, but we are facing with the production of other intermediate species, and that involves also the passage of the transfer of H group. If we want to exploit together oxido and reductive pathway, this was the first reaction that was shown in photocatalysis. So the ability to have contemporaneously oxido and reductive reaction that works, and in this case, it's used to obtain water splitting, so the production of hydrogen and oxygen from water. The first example of this reaction occurred using a single semiconductor. What is important to be able to obtain this double reaction is the fact that both the production of hydrogen and oxygen potential need to be in the middle of the energy gap of our semiconductor. This is the first case, the very original scheme used to obtain water splitting. Now, of course, there are a lot of other processes that occurs. And for instance, we have the famous Z scheme reaction that foreseen the use of two different semiconductors to obtain the separate evolution of oxygen and hydrogen. So I will conclude this talk with a brief focus on what's happened in the case in which we are considered as a specific semiconductor, titanium dioxide, that is the most frequently used semiconductor, and its exploitation for pollutants abatement. It's widely used because of a lot of property that all of you know. And if we consider its energy gap, we have a partial overlap between its excitation bands and the solar spectrum, so we can use a small portion of solar light to obtain the degradation. And what's happened is, in general, and a combination of oxidoreductive processes that lead to the complete mineralization. This is, in theory, what happens in the case of titanium dioxide. In practice, the process is complex. I will not go in detail in all the reactions that occurs because there will be other talks that will be focused on this specific topic. But of course, we have to face with the superficial reaction, homogeneous reaction, recombination, and so on. Processes are a lot. What I want to stress here is the fact that this kind of process is, of course, strongly related to the kind of semiconductor that we choose, but also we have to be very careful with the organic compound that we are choosing. This is the reaction that we want to obtain always, but it is not always obtain something like this. And I just presented 3 very different cases. The first case is a case where we want to analyze, we want to degrade hydrocarbons. In this case, hydrocarbons can be very easily degraded. We have oxidative reaction that permit to burn as a match your chain, so that you are obtaining something that is very close to a combustion reaction, but that occurs at room temperature. This was one of the key reactions where we can see that oxidative reactions are effective in obtaining complete mineralization very easily of our compounds. But if we are consider carbon tetrachloride, in this case, the carbon oxidation state is maximum, so we cannot exploit the use of oxidation processes, and we need to deal with different problems. Since we want to obtain the carbon reduction as the first step to start the reaction, the first thing that we need to do is, of course, eliminate oxygen, as it scavenges most of the electrons. And so we have to work in proper condition. And this is a problem that needs to be taken in consideration anytime that you have something that is not easily oxidized. And in these specific cases, if we start from carbon tetrachloride, we were able to complete mineralize it, even if we start from this starting point that is not so easy. And if we look at the global reaction, what we obtain is in practice an hydrolysis reaction. So we have the complete transformation of carbon tetrachloride into CO2 using a photocatalytic hydrolysis. The first case in which we were not able to obtain complete mineralization was the case of atrazine, where we can see that looking at the TOC, initially we have a very sharp degradation of the TOC, and this is not unexpected since we are dealing with hydrocarbon chains that can be very easily oxidized. But then TOC level off because we are forming cyanuric acid. That is the first case in which almost 30 years ago, in photocatalysis was seen that not all the molecules are completely mineralized. And so starting from then, that period, one of the key challenges has become the try to degrade also these highly stable compounds, and so to try to obtain mineralization for all organic compounds, and not only for most organic compounds. I've chosen all the examples, not checks or other new molecule, since it is expected to be the basis, the first lesson on semiconductor. And so for sure, the other speaker will talk about more recent pollutants, but this problem, even if it's 30 years passes, still remains actual because we have to face with this. Thank you for your attention.